Hi everyone. Sorry I'm not in class today. Just at the dentist for a little work. Anyway, Mr. Tollefson should kind of take you through what needs to be done today. So we're going to continue working on our internal assessments. I just want to bring up the Environmental Systems and Society site. So if you remember down here, we had all our resources down in internal assessment. And what I asked you to do last time was to select a research question, which you guys pretty much did, from the list that I'd given you, unless you want to do something else. And then we went ahead and did the first part, which was the context over here. And the context was pretty much just going ahead and put in the research question and then writing background information there about it. Don't do more than a page. 2-3 paragraphs would be perfectly fine. Make sure that you do citations. Try and do your citations as you go along. It's a lot easier than trying to remember what you did at the end. You should have citations that are both in text and then referenced with a bibliography or a reference sheet at the end there. So that's what we did last time. And what we're going to go ahead and do this time is the next portion, which will be the planning section. Planning section is pretty much like the design section for a classic science experiment. So let's take a look at it right there. I have a hypothesis here. Then we'll talk about variables, equipment, and procedure. And finally, try and do some safety risk here. Let's first of all start about the hypothesis here. So the hypothesis is what you expect to be happening. Now, most of you don't realize there's more than one type of hypothesis. So there is a null hypothesis, and there is also what we call an alternative hypothesis. A null hypothesis, which I've got listed right down here, sometimes it's abbreviated as HO. Null hypothesis essentially means that you won't expect your variable to make any change. For example, suppose I was doing a study on the effect of temperature for carbon dioxide production. My null hypothesis might be, as I increase temperature, I will see no change in the carbon dioxide concentration. Obviously, we're hoping that will not happen, but sometimes it does. Then you want to go ahead and put in an alternative hypothesis. Now, you don't have to have the null, but you should definitely have the alternative hypothesis. This is your main hypothesis. Sticking with my example that I just had a moment ago, I might say, I believe that increasing temperature will give a linear increase in the amount of carbon dioxide production. Now, in the alternative hypothesis, you should also have a reason down there. So I would not just say, I think it's going to increase, but I would say, because of something I mentioned in the background. Because I know that as I increase temperature, I get more collisions, and that increases the rate of reaction. Something on that order. So let's take a look at the sheet that we've been putting together. We've been using the internal assessment template over here. And we should be doing this part right here. Once again, you don't have to have a null hypothesis. Sometimes you might have a project that you've picked where it really doesn't make sense to have a null hypothesis. But you should definitely have the alternative hypothesis, and most importantly, make sure you have a justification for why you think that's going to happen. Now we go ahead and put down variables. I think I've asked this question every day as the years gone on. What's an independent variable? What's a dependent variable? Independent variable is the thing you are changing. Dependent variable is the thing you are measuring. So let's suppose that your research question was, what is the effect of driving cars in Mexico City on air pollution? Your independent variable might be the number of cars, the days that people are driving cars, the types of cars that people are driving, and your dependent variable might be the amount of air pollution, or maybe the amount of carbon dioxide or the amount of sulfur dioxide. There could be more than one dependent variable. Try and keep it simple, though, and only have one independent variable. So go ahead and list down both the independent variable with the levels and the dependent variable. Now, what do I mean by levels? Let's suppose I was doing my temperature experiment again with carbon dioxide production. So that I would say temperature was my independent variable, and the levels of it might be 10 degrees, 20 degrees, 30 degrees, like that. Okay, then you want to go ahead and put down your dependent variable, and once again, there could be more than one dependent variable. Try and keep it simple and not have too many. Finally, we want to do controlled variables. Now, controlled variables are things which, if you did not keep them constant, might change the outcome of your experiment. Typically, people put controlled variables into a table, kind of like this, and you have three different columns: what the controlled variable will be, what level you will keep it constant at, and, most importantly, how will you control it. I gave you just a sample here. You'll delete it, obviously, as you fill in your own. So I said, well, I'm going to do an experiment and keep the temperature always constant at 37 degrees Celsius, which is physiological human temperature. How will I do that? I'm going to do the experiment in a water bath, which has a thermostat. Excuse me. I could do the same for pH, keep it at 7. I could do the same for light, keep it at 60 watts. You should probably try to have, at least 5, 6 controlled variables. Now, don't get carried away. Don't put down things which, they're controlled variables, but they're kind of silly. For example, we're going to do the experiment on the planet Earth. If we did it on Mars, we might have a different result, but I think that's kind of silly for a controlled variable. Now we go down to materials. Materials could be equipment, supplies, any sort of apparatus that you're using. Don't get carried away. Don't put down silly things like water and pencil and paper. We don't want that. You don't have to put your calculator down there, but you want to put down the important things that are necessary in the experiment. Sometimes you want to list the number of them you had. For example, suppose I was doing 100 milliliter beakers. I might say that I have 10 100 milliliter beakers, but some things you don't need to list the number of. Now, the most important thing about materials is you should also list down their uncertainty. Uncertainty means how accurate they are. There are two different ways to do it. One is with digital supplies and one is with analog supplies. So we're down here. Now, how do you know the difference? Well, a digital is something, obviously, that's electronic or something that you're going to plug in. Analog is something that you're not. So, for example, a graduated cylinder, we're not plugging that in. That's an analog supply. Whereas, electronic timer might be a digital supply. Now, how do you know the uncertainty? You look at the increments on there, and the uncertainty should be half of the increment. For example, suppose I had a graduated cylinder, and it was marked off at every 1 milliliter. The uncertainty would be, half of that would be 0.5 milliliters. So we'd indicate it as the uncertainty is plus or minus 0.5 milliliters. This is not the way it is with digital equipment. So if I had an electronic timer and it was accurate, for example, to 0.1 seconds, that is the uncertainty. I don't divide it by 2. I just use whatever the smallest the smallest increment would be. So you want to list down all your supplies with uncertainties. Now, not all your supplies will have uncertainties on there, so don't worry about it. You might have some things that it doesn't matter at all. For example, a scissor. There's no uncertainty on there, right? But if I was using a ruler, for example, and the ruler was accurate, the smallest increment, let us say, was 1 millimeter. Now that's an analog supply. So if the increment is 1 millimeter, then the smallest uncertainty would be 0.5 millimeters. Very important for you to do that. Then we go down to our next part here, which is the methodology or the procedure. Typically, people do these in numbered steps. Don't get carried away. Don't make a really long procedure there. Simple is better. And we certainly don't want to put in silly things like, number 1, gather all supplies. I assume that you're gathering your supplies. And the last step should probably not be record your results or clean up. We just want important things to tell us how to do the procedure. Go ahead and try and write it with using scientific words as much as possible. Don't say silly things like, rip up the sample. We want to use nice words. We want to use words like incubate. That would be a nice way to put things. Okay. Try and break it up into sections if you could. You don't have to. But if there are different sections, one where you're preparing materials, one where you're doing the experiment, try and break it up. If there's a pre-lab, write it as a pre-lab section also. Lastly, we want to go ahead and do some sort of risk assessment, ethical or environmental statement. You don't have to write a lot. Now, sometimes your experiments or the projects we're doing, for example, with databases, don't have a lot of ethical considerations in them. But if there's something where you're using people to do a survey or some chemical that you're using which might be toxic, you want to at least make some sort of mention that you were thinking about it. Doesn't have to be a lot. Let's go back here for a second and let's look at one of our exemplars and see how they did it. I'm going to choose number 2 here. This was a paper about invertebrates and tree density. Let's go ahead and look at their planning section. So I'm going to toggle on down here. Okay, there's their planning section. Here's their hypothesis, and you can see they put a justification with it, right? I expect to see higher tree diversity in the native forest. This is because, so that was really important. They did not put down a null hypothesis here. That's perfectly okay. Now they went down and they put independent and dependent variables there. That's fine. And you can see they went down here and did controlled variables. Now, they didn't put it in a table. Personally, I think it should be in a table. I think they didn't do a great job here on the controlled variables, but that's okay. Now we go down to equipment list. You can see that they did not include the uncertainties there. I think that was a mistake on their list also. They have a risk statement here. That's very nice. And here's their procedure step. They did with numbers. And, oh, this is kind of nice too. They actually included some pictures there to help us understand their procedure. And you can see that their procedure, they actually divided into different parts of their procedure. That's kind of nice too. Now try and be careful when you write your procedure not to put silly statements like repeat for the other levels of the independent variable. We don't have to do that. We already mentioned what the levels are. It's obvious that you are going to repeat it, right? In other words, if I was making chocolate chip cookies, it really doesn't matter how many people I'm making the cookies for or what type of chocolate chips they are. It's really the same procedure each time. Oh, they did a really long procedure on here. I think maybe their procedure actually was a little too long. I'm going to take a look at another one here. Let's go back. Let's take a look at the third one here, UV radiation and rubber bands. Let's see what they did with planning section. Here's their main hypothesis. Oh, so they did more than one hypothesis here. That's kind of nice. You never really know what's going to happen. Some of you might want to do that. Then they went ahead and did their material section. Once again, I don't see uncertainties here. Don't like that. Here's our variables, though. Independent, dependent. Ooh, I really like the way they did this. And there's our controlled variables. Very nice. So I think they did a better job on the variables than the other paper. Here's our method. And once again, we have a picture to go with. And the method is broken up into different parts. Also very nice. There's our ethical considerations. Not much disposal of rubber bands. They may be pushing it a little bit on that. Let's take a look at just one more here. I want to see somebody who did some uncertainties there. Let's take a look at this guy here. Let's see. Oops, this is a different one here. What is this? What is the relationship of let's see. What do we got here? Oh, I'm not getting it on here. Is it way at the bottom? Nope. That link is no good. Let's go to our first guy here. Did he do uncertainties? Let's see. Variables, very good. There's no results. No, hey, none of these guys did uncertainties. Well, I knocked them down a point. Let's see if we can do that to make it a little better than they did. Okay, that's our goal for today, to try and write the planning section if you can.